Hi folks, and welcome back to Educator.com. Today we're going to continue as we tackle the 1998 AP Physics B released examination. What we're going to start today are the free response problems, and we're going to take them in batches of 2 problems each, because there are 8 problems in the test. So we'll do 1 and 2 now, and then we'll take a break and come back to 3 and 4. But for now, why don't we dive in and let's get right into problem number 1. What we have to begin with are a couple blocks, one on a table, the other one hanging off the table, attached by a light string. And to begin with, it asks us to determine the acceleration of block B, the hanging block, as it descends. First thing I'm going to do in a problem like this is I'm going to draw some free body diagrams. So for number 1 here, section A, if I were to draw the free body diagram of block A, I'll have my object. We have its weight, the force of gravity down, the normal force up, and the force of tension to the right. And I'm going to neglect friction because it talks about it being a smooth tabletop. Now for block B, we'll do the same thing. Its free body diagram, we have gravity pulling it down and tension pulling it up. And in this case, we know the tensions of these are going to have to be equal. It's the same string. So let's start and write Newton's second law equation. But as we do this, as it's going to go over the table and down, let's call that the positive y direction. We're going to wrap our axis around the corner of the table. So the Newton's second law in the y direction for A is going to have t going in that direction. And that's just going to be equal to mass A, which is m, times its acceleration A. Let's do the same thing for B. Net force in the y direction for B, well, mg is down in the direction of positive y, so mg minus t equals ma. All right, with those two, t equals ma and mg minus t equals ma, I can combine those. Since they're both equal to ma, I can say t is equal to mg minus t. So let's do that. T equals mg minus t. And then if I solve this, I can find that 2t equals mg, or t equals mg over 2. But wait, I also know that t is equal to ma. So I'm going to replace t here with ma to say that ma equals mg over 2. And if I divide an m out of both sides, I found the acceleration, a equals g over 2. Excellent. Good start. Now for part B, it asks us, it says B strikes the floor. Determine the time at which it strikes the floor. Well, that's going to be a kinematics equation, where delta y is going to be our initial velocity in the y direction times t plus 1/2 ay t squared. And since the initial velocity of B in the y direction is 0, that term goes away. Therefore, I could write this as t is going to be equal to 2 delta y over ay square root, where delta y is just going to be the distance that B falls, which is h, and ay is g over 2. So square root there. That's going to be square root of 4h over g, or pull out the square root of 4, 2 square root h over g must be the time. All right, there's B. Now for part C, it says describe the motion of block A from the initial time until B strikes the floor. Well, during that time, block A is just going to accelerate horizontally across the table. So let's just write that. Block A accelerates horizontally across the table. Terrific. Now on to D. Describe the motion of A from the time B strikes the floor until A leaves the table. Well, in this case, there's no longer anything causing an acceleration, but we also don't have any friction. So it's just going to keep moving at a constant velocity. So I would write block A continues horizontally at constant speed. And we can do that because we already assumed it was frictionless because we said the table is smooth. All right, part E. Determine the distance between the landing points of the two blocks. Well, if we draw our table here, we know that B just went straight down, and A is going to fly off with some velocity, so we need to know this distance, which is really how far A goes as a projectile. So to do this, the first thing I'm going to do is I'm going to find out what B's velocity was right before it hit the ground, because that'll be the same as the initial velocity of A as it leaves the table. So to do that, I'll say that the final velocity of B in the y direction is going to be V initial B plus AY times t. And again, the initial velocity of B was 0, so that's just going to be our acceleration, g over 2, times our time, which we already determined was 2 square root h over g. So that's going to be g square root h over g, or just the square root of h times g. Well, if that's the velocity of B right before it hits the ground, that's got to be the velocity of A just when B hits the ground and when it leaves the table, because there's no friction. So we can say that the velocity, the initial velocity of A in the x direction, which is going to be its final velocity in the x direction too, if nothing's going to speed it up or slow it down while it's in the air horizontally, must be square root of h times g. So now we've got to find the time that A is in the air. Well, to do that, let's go with delta y for A. Its vertical displacement is going to be V initial A in the y direction, which is going to be 0 times t, plus 1/2 AY time for A squared. Its initial velocity vertically was 0. So then, as we solve for t, time for A is going to be 2 tangent of FE over mg, where FE is 0.032 and mg is 0.01 times 10. So I come up with an angle theta of about 17.7 degrees. So now if I want to know the perpendicular distance from the wall, well, let's draw a diagram here. There's our wall. Here is our string of length 0.3 meters. And we know that this angle here we just determined is 17.7 degrees. I can use trig now to figure out the length of this side, our opposite side, which is the distance from the wall. Sine theta, so katoa, sine is opposite over hypotenuse. Therefore, the opposite side, what we're trying to find is the hypotenuse times the sine of theta. Or the opposite side is going to be our hypotenuse, 0.3 meters, times the sine of 17.7 degrees, which is 0.091 meters. All right, that was a little bit more involved. Going on to part D. We're going to cut the string. Oh my. Find the magnitude of the resulting acceleration of the ball and its direction. Well, when we cut the string, we no longer have any tension. Therefore, we're going to have the electric force to the right, which is 0.032 newtons, and we're going to have the force of gravity, mg, which is 0.1 newton. So the total force is going to be the sum of those two. So there's our total force. And we'll try and find that angle theta while we're at it. Well, to find the magnitude, we can use the Pythagorean theorem. That's going to be the square root of 0.1 squared plus 0.032 squared, which gives us a total force magnitude, I should put that around it so that we know we're talking about the magnitude, equal to 0.105 newtons. As far as the angle goes, well, theta is going to be the inverse tangent of the opposite side over the adjacent side, which is the inverse tangent. Our opposite side is 0.1, our adjacent side is 0.032, or 72.3 degrees. So now to get the acceleration. Acceleration is the net force divided by the mass. That's going to be 0.105 newtons over our mass, which was 0.01 kilograms, or 10.5 newtons per kilogram, or 10.5 meters per second squared. And as far as its direction goes, well, if we draw our axis here, we already determined that that's going to be an angle of 72.3 degrees below the horizontal. Moving on to part E, excuse me, or D2. Describe the resulting path of the ball. All right, well, we're going to have a force from the electric field. We're going to have a force from gravity. So we're going to have a net force, and therefore an acceleration, basically that way. A straight line down and to the right. All right, the first two free response questions. If you had trouble with these, I recommend going back to the video lectures previously on those specific topics, checking them out, and then seeing if you can come back to them and do better. In our next segment, we'll do free response questions 3 and 4. Thanks everyone, and make it a great day.